So now that we have established how we've set up a resting membrane potential, now we're going to talk about how that resting membrane potential sets us up for things like graded potentials and action potentials that are going to be transmitting messages into and then down and along a neuron. So again, I'm going to apologize really quickly because I know that my voice is a little off and a little under the weather, but hopefully it'll make it through this whole lecture, because this one is one that you may have to watch 1 or 2 times, because again, we're going to go through kind of the nitty gritties. It's kind of like going through the process of muscle contraction, but here now we're going to be going through this process of nerve conduction, how this actually happens. So when we're talking again about either bringing in these messages or again transferring these messages down a neuron, we're going to be talking about making a change to that membrane potential that we established. So here, our concentrations of the ions across the membrane are going to change. Now remember when we talked about our resting membrane potential, okay, we had here established a concentration gradient of lots of sodium on the outside here of the membrane. Sorry about my horrible handwriting here. And lots of potassium right on the inside, a greater concentration of potassium on the inside. And then remember that we also talked about the fact that the inside of the membrane is going to be more negative, and the outside of the membrane will carry more of a positive charge, okay, right alongside the membrane there. Okay, so keep that in mind as we go through these changes that are going to happen. So again, when we have a change in membrane potential that has to occur for, again, either a graded potential or action potential to occur, we're going to need to change these concentrations of these ions across this membrane. Okay, and then the membrane permeability, obviously, to these ions is going to have to change to allow these ions to move down their concentration gradients, whether it be sodium into the cell or potassium out of the cell. Okay, so changes again in this membrane potential can produce 2 types of signals that we're going to talk about. A graded potential, which is just what it sounds like. It's graded, meaning you can have kind of the gradations of this potential, where you can have small changes to that membrane potential, or we can have larger changes to that membrane potential. Okay, so and these incoming signals are usually operating over short distances, and it's usually over the dendrites because they're incoming signals. Okay, so these are things that we're going to see that happen in the dendrites. Now, our action potentials are long distance signals, and this is what's going to happen when there is, hint, hint, kind of for down the line here, enough of a change inside this membrane here. Okay, and there's enough of a change that occurs that then actually allows the triggering of an action potential. And that action potential is what we call an all or none. Once it's triggered, it's going to travel all the way down the axon. So it's a long distance signal. Okay, we're going to talk about this and how this happens in a little bit more depth here. So changes in the membrane potential, again, are going to be used to receive information, bring it in again through those dendrites, integrate, and then send that information out along the axon and down the axon terminals. Okay. Sorry, I got to exit my drawing here to advance my slide here. So let's get into how this happens. Let's talk first about graded potentials. So now keep in mind that our resting membrane potential is going to be negative 70 millivolts. Okay, so sorry, let me zoom this back out. And so that remember that resting membrane potential is going to always start at negative 70 millivolts. And that is because, I can get my pen to work here for 1 second here. Remember that we have established that electrical gradient, where again, inside the cell, it's going to be more negative up against that membrane, and it's going to be more positive again on the outside. Okay, and so we've established this kind of voltage against the membrane here because it's more negatively charged on the inside, hence the negative 70 millivolts. Okay, and so again, remember that voltage is just measuring the change of that resting potential across the membrane. Now, depolarization, okay, is going to be any time that we decrease this membrane potential, meaning for some reason we are getting a signal that allows a positive charge to move into this membrane, making the inside of the membrane more positively charged, okay? Or again, making a move towards zero. So when we're talking about depolarization, here is a depolarizing graded potential. So again, we started at negative 70 millivolts because again, it's more negative on the inside of the membrane. All of a sudden we had some signal that gave us an influx of some positively charged ions, bringing us up a little bit closer to zero, okay, and then eventually back down. And we'll talk about how this happens. So again, in a depolarizing potential, the inside of the membrane actually becomes less negative, okay? That's key. Becomes less negative than the resting membrane potential was. Now in hyperpolarization, this is going to be just the opposite, right? You're going to get an increase in that, and that's what you're seeing here. This is hyperpolarization. You're getting an increase in the membrane potential away from zero, okay? So you're going to make it more negative. So that's what they mean when they say hyperpolarized. Remember, hyper means like excessive. So now you're making the membrane even more polar. So again, making it even more negatively charged on the inside in comparison to the outside of the membrane, okay? So it's hyperpolar, okay? And so again, this is going to make the inside of the membrane more negative than the resting membrane potential, okay? And we'll talk about why this happens and how this happens. Okay, so it's important to know that, again, as we talk about graded potentials here, oh, I'm sorry about that. My pen, for some reason, it wants to zoom here. But the important thing is to remember that graded potentials are actually going to be occurring in the dendrites most often, okay? And then also the cell body of the neuron. So when we talk about graded potentials, we're going to be talking about, again, localized changes. And graded potentials are really going to be localized changes that are occurring in the dendrites as well as the cell body, okay? And so when we talk about an action potential, okay, an action potential is going to be in the axon. So keep that in mind as we kind of go through this lecture. Sorry, hold on 1 minute. Wow, I'm really having trouble with my bamboo today here. Okay. So excuse me while I fuss with this for just a second here. So when we talk again about these graded potentials, again, they're short-lived, they're really localized changes, and again, they're going to be primarily in the dendrites and the cell body. The stronger the stimulus, the more voltage change that occurs and the farther the current flows, okay? And this is going to make a little bit more sense in just a minute when I kind of draw this out and put this all together for you. Again, it's going to be triggered by a stimulus that's going to open gated ion channels, again, allowing either a positively charged ion in to cause depolarization, or again, the opposite, it might be allowing positively charged ions out, which could cause hyperpolarization. Okay? And then, again, it's oftentimes going to be named according to the location and the function. So a receptor potential is going to be a graded potential in receptors of sensory neurons. Okay? That makes sense, right? receptor potential. Again, it's occurring in the receptors of sensory neurons, sensory receptors, okay? And then postsynaptic potential is going to occur in the dendrites of a neuron, again, that's met up with another neuron. So postsynapse means, again, on the receiving end of synapse with another neuron, okay? And so we'll try to make sense of this here in just a minute. So what happens again in some type of, again, graded potential here is you'll see you get these very localized changes. So again, for some reason, you get a stimulus here, okay? It could be a mechanical stimulus. It could be a chemical stimulus, like a neurotransmitter that is binding. But you're going to get some type of stimulus, let's say, in your dendrite here, okay? And in this case, let's say it's a mechanical stimulus, and literally, the pushing on that sensory receptors there is actually causing these these ion channels to open, these mechanically gated ion channels to open. So literally, when you push on that, that gate opens and allows sodium to rush in. As sodium rushes in, it's going to cause a very localized change or depolarization in the inside, the interior of the cell here in that area, okay? And so then we'll talk a little bit about how that depolarization is passed on. So how do graded potentials arise? And so I kind of touched on this, in that our source of our stimulus can be either mechanical, a stimulation of the membrane, again, with these mechanical gated ion channels. And what this literally means is, let's say we have a receptor here and, an ion channel here, and here's our ion channel in the membrane here, right? And it has, this, again, mechanical gate here, okay, that is keeping, maybe sodium out from rushing in. And what ends up happening is when put pressure on this, okay, it can actually basically cause the ion channel to kind of temporarily deform and allow that gated ion channel to actually open. So again, sorry, I know I'm having trouble here with this. I don't know why it's very touchy today. But it would actually cause, if you can picture, you push on this and it causes this to kind of deform a little bit and causes a gap in here that actually allows sodium. Oh, sorry about that. Again, it's just really frustrating today. But I really need my drawing function to kind of show you how this works. But if you can just picture again, it causing, again, that gate to kind of warp a little bit, allowing ions in. That's what your mechanical gated ion channels are going to do. And that's how we're going to stimulate these sensory neurons based on, again, these receptors like touch receptors and pressure receptors. Now, chemical stimulation, again, is going to be kind of what you're more familiar with, again, a neurotransmitter. So again, this is where a neurotransmitter is going to bind to a receptor on that ion channel. And when it does, it's going to open that gate, okay, allowing the ions to come across that membrane. Now, again, graded postsynaptic receptors or generator potentials, again, all these different names for this. It's just basically allowing ions to flow through these channels and change the membrane potential, okay? But it's going to be locally. It's changing the membrane potential locally, okay? So that's our graded potential. And the amount of change, again, is going to vary with the strength of the stimuli. So the more pressure, again, you're putting in that area, the more of a stimulus you're putting in that area, the more of these channels are going to open, right? Okay. And so again, the amount of change is going to vary with the strength of that stimuli. And again, this is going to be local, okay, because this is graded. So let me go ahead and get you to the next slide here. So I really like this diagram because it kind of puts it all together. So in here, what's going to happen is we need to get these graded potentials, okay? Again, in the dendrites and the cell body, to hit a threshold point for an action potential to occur, okay? Now, we haven't really talked about this yet. I'm just going to kind of introduce this here, and then we're going to get into action potential in just a minute. But we have to hit this threshold point here, and this threshold is going to be at a point that is about negative 55 millivolts, okay? So remember that here, our resting membrane potential here is going to be around 70 millivolts, okay? But to cause an action potential, and remember, action potentials only happen, think A, action potential only happens in the axons, okay? Did that, we need to be able to bring, again, that voltage potential across the membrane up to about negative 55 millivolts, okay, for an action potential to occur. So negative 55 millivolts, okay? If you can see my horrible writing here. And so how that is going to happen is that we have to cause enough of a change here in the dendrites and the cell body so that this point right here, again, where our trigger zone is, oops, let me pull on my pen again. So our trigger zone here will have to hit this threshold point. So what I mean here is all along here, right, we have these gated channels and all along our cell membrane. And again, remember, it's going to be more positively charged on the outside and more negatively charged on the inside, okay? Now, please keep in mind that there are both excitatory and inhibitory, okay, graded potentials that can happen. So we can either cause localized depolarization, okay, making it, again, bringing us closer to that threshold point, or we can cause hyperpolarization, which brings us farther away from that threshold point, okay? And so what happens is this is a combination, right, of these. So maybe you get some inhibitory neurons that are innervating this one here, and they're putting off some inhibitory neurotransmitters. And those inhibitory neurotransmitters are maybe allowing a potassium gated channel to open, allowing this positively charged potassium out. Again, if that happens, right, we're pulling positive charges out, making it even more negative in comparison to the outside of the membrane, right? And so in that case, we're here. We're getting farther away. We're making it more negative and farther away. But then maybe we have some excitatory, again, some excitatory neurons here. And instead, they're opening up sodium-gated channels and letting sodium rush in. And as that sodium rushes in, again, we have all these positively charged ions coming in. It's going to make it more positively charged on the inside of the membrane here. And that is going to, again, bring us closer to zero and closer to our threshold point, okay? So again, sorry, I don't know what happened to my negative 70 millivolts here, but that negative 70 millivolts is our resting. And then here we need to get to negative 55, right? Okay. So now it's a combination, right, of what's happening in our dendrites and all of the, again, different neurons that they're interacting with. So of course, this is a multipolar neuron. And so it's interacting with all these different neurons. And some of these synapses might be excitatory, or these neurons that it's synapsing with are excitatory, and some are inhibitory. But it's kind of a combination. And let's say if we have more excitatory neurons, right, that are producing more of a change inside than the inhibitory ones, then what's going to happen is we're going to all of a sudden be bringing in more positively charged ions than are leaving. okay? And as we bring more and more in these localized areas, and maybe again, we have another neuron here that's causing again an excitatory potential and more positively charged ions to come in. And so we're really again bringing ourselves closer to threshold. So if we cause enough of a change in the dendrites in the cell body here, to where we are closer, enough of a depolarizing, again, right? Graded potentials are occurring, enough of these depolarizing graded potentials are occurring, and again, bringing enough of a change on the inside of the membrane here, closer to that threshold, then once we hit this negative 55 millivolts, okay, and that's, again, spread to here at the trigger zone, now we can trigger an action potential. And an action potential is an all or none deal, meaning once we trigger this action potential here in that trigger zone, now that action potential will move just like we talked about again, right? It's in an axon. It's going to move all the way down the axon, okay? So that's the point of no return. This negative 55 millivolts, if again, enough graded potentials allow us, enough excitatory graded potentials cause enough depolarization that we eventually, again, hit this negative 55 millivolts right at that trigger zone, boom, an action potential is generated and it is moving all the way down that axon, okay? And there's no stopping it, all right? So an action potential, again, is going to occur if the combination of all these graded potentials finally exceeds the threshold of negative 55 millivolts, okay? So hopefully I really like this. I know it's not from your text. I kind of took it from another text, but I really like how it kind of puts it all together to make sense of that. So again, keep in mind that an action potential, again, is going to be a rapidly occurring event, and it is an all or none event. Once we stimulate an action potential, it is in the axon and it is moving all the way down, okay? And we'll talk about this action potential and how once the action potential moves all the way down to those, again, axon terminals where it's going to stimulate the release of neurotransmitter, then it will come back and repolarize itself and get ready for the next action potential, okay? So again, an action potential it follows the all or none principle, okay? And we'll talk more about this as it kind of goes on as we go through the lecture here. Okay, so let's talk about the events that occur in an action potential in this kind of step-by-step process. And then I'm going to put the two together on just a drawing that I'm going to put together for you, okay? So let's talk about the events that have to occur for an action potential to occur. So let's say that we created enough of a change, again, at that trigger zone from all those graded potentials, and we ended up having enough of a depolarizing stimulus and enough positively charged sodium ions coming in that we hit this negative 55 millivolt point. And I got ahead of myself because they start here with the resting state. So again, prior to hitting that threshold at that trigger zone, okay? So let's say, again, we had all those graded potentials that are happening, but we haven't hit that threshold in that trigger zone. Prior to that, in the axon, if you look down on the axon, all of the channels in there are going to be in the resting state, which means all of your gated sodium channels and your gated potassium channels are closed. Now remember, we still have the leakage channels and we still have a lot of, well, I shouldn't say a lot. We still have potassium leaking out. We still have a little bit of sodium leaking back in so that we establish that resting membrane potential, right? And again, we have the sodium potassium pump that's keeping lots of sodium on the outside and again, lots of potassium on the inside. So that's our resting state, okay, established and ready to go. So again, the four main states here are that all of the gated sodium and potassium channels are closed here, okay? We saw that. Only the leakage channels for sodium and potassium are open. We just talked about that. Each sodium channel, again, is going to have 2 voltage sensitive gates. We haven't talked about this yet. It has one that's called an activation gate and That one is going to be closed at rest, and it's going to open because it's an activation gate. So it's going to open with depolarization, allowing more sodium to enter the cell. And then the inactivation gates are going to be open at rest. You're going to see these are going to be important because they're going to block the channel. Once the activation gate has opened and allowed some sodium in, then the inactivation gate is going to close and prevent more sodium from entering this cell while repolarization happens. Okay, so I'm just kind of introducing these now, but this will make more sense as we kind of go through this. So I just want to introduce that there's actually two actual gates here, and you'll see this. They're going to show you that in this image here in just a minute. So, okay, let's say again that in the dendrites, again, remember we're in the axon here, but over here in the dendrites in the cell body, we ended up having enough depolarizing graded potentials that allowed, again, us to hit this negative 55 millivolt threshold potential here at the trigger zone. And once we hit that trigger zone, now depolarization is going to happen. So that's going to trigger, and these are going to be voltage gated channels now. So again, remember in our graded potentials, we were talking about a ligand gated or chemical gated channels and mechanical stimuli, right? Mechanical gated channels. But here in the axon, these are voltage gated channels. And so now that change across the membrane in membrane potential from negative 70 to negative 55 millivolts is what's triggering these neighboring sodium channels to open. So now this neighboring sodium channel opens, allowing sodium to rush in, okay? As that sodium rushes in, remember again, we originally had this negatively charged interior, right? And the positively charged exterior. So now, as that sodium rushes in, it's going to cause, again, a change in this area, now the trigger zone of the axon, bringing in this more positively charged ion, okay? Now, as this happens, this is going to trigger neighboring sodium gated channels to open, okay? And this is when it triggers these neighboring, because again, we're causing, again, a change in membrane potential, again, right here, right? So this is going to trigger these neighboring gated sodium gated channels to open, allowing even more sodium to come in, okay? So there's your depolarizing or depolarization phase. Now, our next phase, okay, here, sorry. And so here's the slide on, because you guys don't have, not all of you have a textbook, these are my kind of slides with the verbiage on it. So again, depolarization is where sodium channel opens. Again, it's depolarizing local change when we open these voltage gated channels, these voltage gated sodium channels, sodium rushes into the cell, right? The sodium activation and inactivation gates are both going to open. So the sodium, again, influx into the interior is going to cause, again, a change in that membrane potential, making it more positive on the inside, okay? So then, again, at threshold, negative 55, they say negative 55 to 55 millivolts. So again, I'll usually say negative 55 millivolts because that's kind of what most of the books say. But again, it's somewhere in between negative 55 and 50 millivolts. Again, this is going to cause a positive feedback mechanism in the axon, because what's going to happen is it's going to trigger as that sodium gated channel opened, okay, because the neighboring area in front of it hit that negative 55 millivolt threshold. Now it's going to cause more sodium to rushing in, causing the neighboring channels to open, causing more sodium to rush in, causing the neighboring channels to open, causing more sodium to rush in. So remember, this is a positive feedback mechanism, and this is going to result in a large action potential spike, okay? So typically, again, they tell you that the membrane polarity is actually going to jump from, again, what was initially that negative 55 millivolt threshold all the way to like positive 30 millivolts. So again, that's your depolarization, allowing that sodium rush in. Now, once we hit that peak, okay, where we've all of our sodium gated channels in this localized area have opened, then we're going to hit what's called repolarization. And in this case, what's going to happen is the inactivation gate is going to close, okay? And that's because it's going to make this area inactivate. Okay, and this is really important because this has to allow repolarization of the membrane to occur. And that's because we want to get it ready for the next action potential. Okay, so again, this inactivation gate is going to close, and that means it's inactivated, this channel here. It cannot be reactivated for a short period of time. Okay, at the same time, the potassium channels are going to be triggered to open, now allowing potassium to rush back out. Because remember, we just made the inside of the membrane much more positive, okay, close to like positive 30 millivolts. So now we need to return the membrane to the interior to a more negatively charged state by releasing positively charged ions out. And we have to, of course, use our concentration gradient. So since we have lots of potassium built up on the inside of the cell, our potassium channels make sense, right? So our potassium channels open up, potassium, and then is going to then move through this voltage gated channel. Again, the voltage change in voltage is what triggered this potassium channel to open, allowing potassium to move out, allowing the membrane inside to become more negative once again, and restoring our membrane potential, okay? So let me go to the next slide here, and it'll kind of give you all the verbiage on it. So again, repolarization happens here. Sodium channels are inactivated because that inactivated gate is going to close, and potassium channels are going to open. Okay, so sodium channel inactivation gets closed, and this means that we cannot trigger that to open for a short period of time, and our action potential spike stops. And then as potassium exits the cell down that electrochemical gradient that we've set up, repolarization is going to occur, and we're going to return to our resting membrane potential. Now, why do you think we have this inactivation gate versus our activation gate? You'll see in just a minute. This is the activation gate. Why do we have this inactivation gate here? If we are in an axon, if we're in an axon here and we want we want to pass down our signal down our axon this way, down this way here, okay? Why is it that we are going to render this channel inactivated once we've again caused a depolarizing effect across the membrane here? Okay, and the reason is, if you think about it, it makes sense, right? We want to propagate this action potential this way. We don't want it going back this way, right? So as we're bringing in sodium and it's rushing in here, okay, sodium rushing in, and then here again, it's triggering these neighboring sodium channels again to bring in more sodium, okay? For this part of the membrane to repolarize, and again, for us to transmit this message in one direction, we need this sodium channel to close, okay, and allow repolarization to occur. And that can't happen if this voltage gated channel can keep being triggered open by its neighboring sodium gated channels that are allowing, again, a depolarizing potential, okay? So this allows us to transmit that message in one direction, okay? So I just wanted to, I know I'll introduce that in another slide, but I wanted to introduce it here too, because I think it just helps to kind of put all the pieces together. Okay, so again, we went through the first phase, which was the resting state. Then we went through depolarization. Now we've gone through repolarization, bringing us to this point, back to, again, our resting membrane potential. And then we're going to have what's called hyperpolarization, okay? And that's where we actually let so much potassium out that it actually brings us below the point of our resting membrane potential. So below that negative 70 millivolts, okay? And so again, some of these potassium channels remain open. And so finally here, our sodium channels are going to reset. So our inactivation gates are finally going to release and our activation gates are going to close. Now, this sodium channel can then be triggered by another change in membrane potential, okay? Now, at this point during hyperpolarization, until this kind of evens out here, at this point right here, it's going to take a greater than threshold change to trigger this sodium gated channel, okay? But it can be triggered, okay? Because once that inactivation gate is released, then the activation gate can be triggered. It just has to hit that negative 55 millivolts, okay? So again, some of our potassium channels are gonna remain open. Our sodium channels are gonna reset themselves. And so those potassium channels actually allow kind of an excess of potassium out. And the inside of the membrane actually becomes more negative than when it's in its resting state. This is called hyperpolarization of the membrane. Again, it's a slight dip below the resting membrane voltage. And this, again, gives us time for those sodium channels to reset, but also then it gives a little bit of time in between, action potentials, and that you really have to have a really strong stimulus that's causing a really big change for us to be able to hit threshold if you're all the way down here, okay? So then what brings us, you're like, okay, well, those sodium channels again are open. What brings us back to resting membrane potential? So what happens is then those sodium channel, or I said sodium, I'm so sorry, potassium. Those potassium channels here that were still open are going to close. And as they close, our sodium potassium pumps are going to reestablish our ionic conditions. So what that means is that, again, as this potassium channel, this gated channel eventually closes, okay? Oops, I'm sorry. I thought I had my pen on. But if you can picture, again, this is going to close. As it does, our sodium potassium pumps are going to come back into play here. And what that means is we still have, I know it's hard to picture all this happening, but we do still have these sodium potassium ATP pumps here that are going to then pump the sodium back out. So 3, oops, my pen doesn't want to draw there. 3 sodium back out. Remember, these require ATP because we're pumping against a concentration gradient here. So 3 sodium here out for every, how many? 2 potassium back in, okay? So again, the potassium that just left is going to be pumped back in, 2 potassium back in, reestablishing our ionic gradients and reestablishing, again, our electrical gradient as well, okay? As we pump more positive charge out than we do in, and remember, we have those potassium leakage channels too, okay? So again, this is going to allow us to reestablish our resting membrane potential. So that's happening right here, okay? So hopefully that kind of makes sense to you. Okay, so let's get on with it. So here it is all put together, okay? And so what I want to do is I want to take this blank slide for a minute, if my pen will cooperate, and I hope it does. And I want to kind of draw this all out for you in terms of what is going to happen for this whole process. So here I'm going to draw, it's going to be a horrible neuron. I'm not going to promise anything special because one, my bamboo is, I think, just old, and it is really tough to draw on these days. I'm sure they have better ones now. Okay, so here is, and it also is very slow. So here is my axon. And here is the end of my axon, and it's going to end in these. Man, it really does not want to draw. I'm so sorry for that, guys. It's going to end in these, again, axon terminals. Again, sorry, this is the best I can get with my bamboo here. And if you can picture, again, these axon terminals are going to have these synaptic end bulbs, right, that are attached like that, okay? So here is my dendrites and my cell body, okay? And so again, let's say that we have these other neurons, okay, that are going to send an excitatory message here. So here's my other neurons, and again, you'd have more than one, okay? And here is my synaptic end bulb. And in this case, these neurons are releasing, okay? And again, there would be many. There would be one here. There would be maybe another one over here. And these excitatory neurons, okay, maybe we're sending, again, a sensory message here to send information back again to the brain. And in this case, maybe it's, again, touch receptors or something like that, a mechanical receptor. But anyway, either way, it's going to cause an excitatory potential or depolarization. So again, remember that all across this membrane, we are at resting membrane potential. And let's draw that really quick so that we can see that we are all across this membrane at our resting membrane potential. More positive on the outside than we are on the inside, right? And so again, we're at our resting membrane potential. Man, my pen is really having trouble today. At negative 70 millivolts, okay? Negative 70 millivolts. And this is going to be all across the membrane. So that means this is going to be all down the axon as well. If I can, oh man, get my pen to work here. Wow, it really is giving me trouble today, of course. So here is going to be negative all down the membrane here. Down here, down here. And again, more positively charged on the outside, okay? I'm just going to put a bunch over here just to kind of remind you. So that's our starting point, okay? So again, we all of a sudden are getting these excitatory signals from maybe, again, a touch receptor on your finger, and it's going to cause these gated channels to open, causing, again, sodium to rush in, okay? So again, remember we have this also chemical gradient established as well, because it's an electrochemical gradient. So we got lots of sodium on the outside, and again, lots of potassium built up on the inside thanks to those sodium-potassium ATP pumps. So again, with these excitatory potentials, okay, all of a sudden we cause these sodium-gated channels to open up, allowing sodium to rush in. As that sodium rushes in, okay, it's going to cause the interior of this membrane to become more positively charged, triggering, again, even these neighboring sodium channels to open, some of those voltage-gated channels to open, allowing sodium to rush in, okay? And here we got another, again, synapse that's triggering an excitatory potential, causing sodium to rush on in here. So what ends up happening is if we get enough of a change in membrane potential, boom, it's all these positively charged ions kind of hanging out here, and they hit this area called the trigger zone or threshold, the trigger zone of the axon, this initial segment, the trigger zone. Then what happens here is if enough of a change occurs and we hit that negative 55 millivolt, because we've caused enough positively charged ions to come in, if we hit that threshold here, we are now all or none, okay? We have triggered an action potential, and there is no going back from that. Once we trigger these sodium-gated ion channels to open with that change in voltage at negative 55 millivolts, so here I'm going to put negative 55. We hit that negative 55 millivolt point, it is an all or none deal. And now that action potential is going to go all the way down the axon. So what's going to happen here is we've triggered these sodium-gated ion channels, okay, to open up their activation gates, okay, because they're activated by that change in membrane potential. Now, sodium is going to rush in here, okay? You can see this from my diagram, okay? And as that sodium rushes in, it's going to trigger these neighboring sodium voltage gated channels, okay, to open as it brings this membrane potential up to negative 55 millivolts, right? In this area. So now in this area, okay, we've triggered all of the sodium gated ion channels to open. And now here, that's going to cause, again, more of a change, more positively charged ions to come in here. And now they're going to trigger these neighboring ion sodium gated channels here to open up, okay? Causing, again, sodium. And so you can see how this would propagate down this way, right? We're propagating this action potential down this way. So again, as we are going to be triggering these neighboring sodium voltage gated channels to open as we get these localized changes to negative 55 millivolts, these localized depolarizing changes, right? Okay. Now, what's going to end up happening is eventually that action potential is going to make its way all the way down here. And then here, eventually, we're going to trigger, okay, the release of neurotransmitter, okay, here. And that neurotransmitter will be the way in which we pass that message from one neuron to the next, okay? So again, I'm just getting into a little bit of this because I just like to, we'll talk more about this in the next lecture on how this happens, but I just like to kind of introduce that, and that's how that happens, okay? Now, obviously, we don't want this action potential to just keep firing, right? We don't want to keep this going all the time because we want to make sure that it's only firing when it's getting the stimulus. So what's going to happen then is after a depolarizing effect occurs here. So after depolarization, okay, remember we're going to hit repolarization. So let's say again, we hit at that point where enough sodium rushed in that we hit a point that it was so positive, it was about positive 30 millivolts in the interior of the membrane here, okay, because we made it more positive in the inside of the membrane. And so as that happens, again, our inactivation gate is going to be triggered in our sodium gated channels here, okay? As the inactivation gate is triggered, that means temporarily this sodium gated channel cannot reopen. So it closes, okay? And that way then it forces the action potential down this way. Now, as that closes, I need another color here. Hold on. Let me see if I can get another color here. I'm going to try yellow here, okay? Hopefully that's, or maybe green. That's enough of a change. So as those sodium gated channels close, especially again, that inactivation gate is closed. Now what's going to open? You got it. Potassium. And potassium, as that voltage gated channel opens for potassium, potassium is going to rush out, okay? And as that potassium rushes out, we're going to have positively charged ions leaving, returning this interior of the membrane to be more negative, okay? And that is our repolarization phase of the neuron. And that's going to happen all along, okay, that axon following depolarization at each of these sections, okay? And then, remember, eventually, in that hyperpolarization phase, our sodium channels are going to reset, which means that inactivation gate will be released and the activation gates are going to be closed. And that excess potassium will kind of rush out, really giving us that hyperpolarized effect where it's going to drop to a point where so much potassium left out, it's going to go even more negative than negative 70 millivolts. Okay, so it's going to become hyperpolarized, okay, hypernegative on the inside. And that just means that for that activation gate now, for that sodium channel right here, it's going to take a greater than threshold, okay, stimulus to bring us to a point where this sodium gated channel will open. So that gives us a little bit of like what we call a refractory period, a little bit of a break before, again, this neuron can be re-stimulated, unless we have like super strong stimulus that can open up that sodium-gated ion channel, okay? And so that will bring us back to that repolarization. Now, when this potassium-gated channel closes, when that closes, then what's going to bring us back to normal is those sodium-potassium pumps, the sodium-potassium ATP pumps, okay? Now, you may say, okay, well, the sodium-gated channels and the potassium-gated channels are both voltage-gated channels. So why does one open first and then this potassium right next to it open second? And the reason is that they're both triggered at the same point in time. But what happens is the sodium-gated channels open and close quickly, and the potassium, when it's triggered by that voltage change, it's going to slowly open, okay, really slowly, kind of like a creaky door. So again, by the time here a voltage change occurs, we hit negative 55 millivolts, we got that trigger point. Both of these, both the potassium and the sodium-gated channel here are going to be triggered open. But the sodium-gated channel is going to open quickly. And then as that inactivation gate closes, okay, after it's already let sodium rush in, the potassium-gated channel is going to finally creak open all the way, okay? So again, they're both triggered by that voltage change. It's just sodium open and closes fast, okay? And potassium, it opens so slowly that it's not open until that the sodium is already rushed in and that inactivation gate is closed, okay? So I don't know if that helps to make sense. Not necessarily a point that you have to know, but I think it helps to make sense of how they're both triggered by that voltage change, okay? So again, I'm going through this in terms of lots of different ways in which you can kind of get through an action potential. So I love this graph because this is showing you what happens at kind of one spot on the axon, okay? And I like it because it relates it to what's happening in each of these phases. So here in purple, right here, is the resting membrane potential. So the voltage-gated sodium channels are in their resting state, and the voltage-gated potassium channels are in their resting state closed. Okay, the only thing that's open is leakage channels here. Okay, and our resting membrane potential is negative 70 millivolts. Okay, good, everything's happy. All of a sudden, we get a stimulus. Boom, right here. Okay, and that stimulus is enough to bring us to threshold. Okay, so again, you know, maybe some sodium-gated channels were opening there. Again, and graded potentials brought us to this negative 55 millivolts. Okay, now we have hit the all or none point. So now that negative 55 millivolts is going to trigger our voltage-gated channels to open. Remember, the voltage-gated sodium channels are going to open first, and because they're going to open fast. And so that's what's going to happen during our depolarization phase. Voltage-gated sodium channels, activation gates are going to open, allowing an influx in of sodium into the cell, okay? All the way, and as that sodium rushes in, it's going to, again, cause a depolarizing effect, bringing the membrane potential all the way up to about positive 30 millivolts, okay? Now, at that point, the inactivation gates are closing for those sodium-gated channels. And now, finally, those, remember, creaky potassium-gated channels are finally open, and they're going to allow potassium to rush out, okay? And as that potassium rushes out, it's going to return that negatively charged membrane potential, okay, back to eventually our resting membrane potential at negative 70 millivolts, okay? Now, in this state, again, our sodium channels are inactivated because the inactivation gates are closed, and those cannot be triggered to open, okay? Then we're going to hit now what's called our hyperpolarization phase, okay? And here, this is just where our, again, potassium channels have stayed open, and they've allowed a little excess potassium out, which brought us below that 70 millivolts, okay? And now our sodium-gated channels are basically reestablishing themselves here, okay? And so as they do that, those sodium-gated channels they can be triggered to be open because now our inactivation gate's open and our activation gates are what's closed. And it can be triggered to be open, but look at this. It has to go now, it's below negative 70 millivolts. So instead of this stimulus, okay, it's gonna take this type of stimulus to hit threshold. And so we actually call these are two different refractory periods. This refractory period is called a relative refractory period because it's relative to whether or not you get enough stimulus to re-stimulate that sodium channel to open during this period, okay? Now, eventually, again, remember that those potassium-gated channels are going to close, and eventually we will be brought back to resting membrane potential, okay? So this is just a short refractory period. But this one's relative to, again, our stimulus that it's occurring. Now, our absolute refractory period is absolute. And that's when, again, this is a period where our inactivation channels and our sodium channels are closed, okay? Or again, and also during the activation phase because it's already activated. So again, you can't activate that channel to open any more than it already is. It's already open, okay? But I like to think of the absolute refractory period as, again, you absolutely cannot stimulate this channel, okay, to reopen at that point. And that's because, again, that inactivation gate's closed. So this is that absolute refractory period, okay? That inactivation gate is closed until, again, the repolarizing phase is, until the repolarizing and hyperpolarizing phase occur. Okay, so again, I just like to introduce it. I know I'm gonna hit that a little later, but I'm introducing it all now, and then I'll kind of round it out as we go through each of these, okay? Okay, so I'm gonna and hopefully it does a better job than last time. I apologize. For some reason, I don't know why when I played this the last time, it had like two different sound bits. So we're gonna try this again. But I really like these animations, and I'm afraid that you won't watch them. So I'm afraid I'm hoping that if I put it in here, that you might actually go back and watch it. So let's go ahead and go through this. These are great animations because it summarizes everything.
Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary. Generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
Okay, so how great is that animation? I love that animation because it just really summarizes everything so well. Okay, so again, just as but these are just kind of the verbiage slides. Keep in mind again that remember that when we're talking about an action potential, not graded potentials that are happening in the dendrites and the cell bodies, but here we're talking about an action potential on the axon. It is an all or none deal, okay? So again, for the axon to fire and an action potential to go all the way down that axon, depolarization has to hit that threshold of around negative 55 millivolts, okay, to trigger an action potential. And once that happens, again, remember it's a positive feedback cycle, then again, what's going to happen is those sodium-gated, voltage-gated channels are going to open, allowing sodium in to rush in, causing more of a voltage change across the membrane, causing neighboring sodium-gated channels to open. So again, it's all or none, okay? And so again, this is the analogy to this is kind of like the squeezing a trigger. If you squeeze a trigger harder, it's not going to make the bullet go any faster. Okay. So again, and that's the case with your action potential. As long as you hit that negative 55 millivolts, and then, it doesn't matter if you are negative 50 millivolts or negative 45 millivolts. You've already hit that threshold. And once you hit that threshold of negative 55 millivolts, again, that action potential is moving all the way down the axon and you're not stopping it, just like you're not stopping a bullet, right? Okay. So that's the kind of analogy for the all or none the propagation. Now, again, once initiated, an action potential is self-propagating. And this is going to be a little bit different. And now we have to think back to the non-myelinated axons. We've pretty much just been talking about how it works in a non-myelinated axon, right? But propagation down an axon can happen in the myelinated axons. It's just going to jump from node of NVA to node of NVA. And we'll talk a little bit about how it does that either in the end of this lecture or at the beginning of the next one, okay? But we know that an action potential is self-propagating, and that's because, again, as those sodium-gated voltage channels open, allowing sodium to rush in, causing the depolarization of the membrane in that one area, it's going to trigger these neighboring sodium-gated channels to open, right? And it's going to propagate that action potential down the axon, just like, again, if you've ever seen like at a stadium where they start the wave, and then again, that wave propagates, right, down the stadium. That's exactly how an action potential is propagating, okay? So again, if you can picture it happening like that with these sodium-gated channels opening, okay, allowing sodium to rush in, triggering the neighboring sodium-gated channels to open, again, allowing sodium to rush in, triggering the neighboring sodium-gated channels to open. And as that action potential travels, it travels all the way down that axon, but only in the forward direction. So again, why does it travel only in the forward direction? Remember, we have those inactivated gates, those inactivation gates in the sodium channels to thank for that. Because once this sodium-gated channel, here, I'm going to get my pen out here. So once this sodium-gated, it doesn't want to give me my pen. I don't know why. But once this, there we go. Oh, now it won't let me advance back. Hold on. Sorry. Let me go here. Oops. Let me go back here to this slide here. So what happens is here at this point, once we trigger this sodium gated channel to open again, after it opens and allows sodium to rush in, the inactivation gate is going to close and it can't be re-triggered for a short period of time. That's the absolute refractory period. So it forces the action potential down this direction, okay? So it forces it to move in that forward direction. And this traveling action, this traveling action potential that goes in that one direction is called a nerve impulse, okay? Woohoo! We got there. We got the nerve impulse. Okay. So hopefully now it's starting to make sense. Okay. So again, propagation allows an action potential to be transmitted from its origin down the entire axon length toward its terminals. Okay. And again, that sodium influx through these voltage gated channels in a membrane area causes local currents that cause the opening of neighboring sodium gated voltage gated channels to open in, again, these neighboring areas. And so again, this is just all the verbiage of what I've already told you. Again, I have it written out because you don't have necessarily a textbook. I know some of you do, but many of you don't. Okay. And so that's what you're seeing here. And this is the great part, is that it's showing you again, this propagation of an action potential. And again, as these sodium gated channels are triggered to open because threshold was met, okay, then it's going to trigger the neighboring sodium gated channels, the voltage gated channels, to open, right? Allowing it to become more positive until it hits threshold, triggering the neighboring sodium gated channels to open, okay? And again, it's propagated in only one direction because here, the sodium gated channels here that were just open, they're in that absolute refractory period right now where the inactivation gets closed and they can't be reopened, okay, for that short period of time. So again, that's why it happens in that one direction. So here, I'll go ahead and play this propagation video for you, and then we'll go ahead and stop here. Okay, so again, another great A&P flicks from
Action potentials propagate
the Marieb text, the Pearson text.
An action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So, action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way.
Okay, so I wanted to go ahead and let that play because that is my next step here, which is saltatory conduction. And saltatory conduction is just the way in which, again, we're going to propagate an action potential. But remember that, again, most of our neurons are myelinated. And so we're going to talk about how they kind of jump, that action potential kind of jumps down from node of RNVA. And it's actually pretty easy. Once you've gotten this hard part done of learning how an action potential happens, the rest of this is actually fairly easy. So really quick, this is kind of an important point, and I want to make sure that I bring this up. All action potentials are alike, right? Because basically, again, once you've hit threshold, the action potential is going to go all the way down the axon, okay? So how does the central nervous system tell the difference between a weak stimulus and a stronger stimulus, okay? Like a light pressure versus deep pressure, okay? And the way that it does that is by the frequency of impulses, okay? So it's the frequency, because it's not like you have like a bigger action potential. All the action potentials are the same, right? They're all the same. They're all or none. So it's the frequency of these action potentials per second. So how quickly, again, that that neuron is re-stimulated and that action potential starts up again. Okay, so how many of those action potentials we have per second is going to differentiate between a weak stimulus, which would have fewer impulses per second, and a really strong stimulus, which would have more impulses, right, per second. Okay, so higher frequencies mean stronger stimulus. Okay. This is just going over, I already went over this because I drew out my big picture, but this is just going over the absolute refractory period versus the relative refractory period. So remember, the absolute refractory period is due to those inactivated sodium channels, the inactivated sodium gates, because they can't be activated by anything at that point. And then the relative refractory period is just because of this hyperpolarizing effect, which means it just takes what we call super threshold stimulus. So a really strong stimulus, right? To cause, again, not just this change right here, but now this change here. Okay, so we call that super stimulus or super threshold stimulus to start that next action potential. So again, the potassium channels are still open, but the sodium channels have closed, and now it's just their activation gates that are closed. Okay, but the inactivation gates in this relative refractory period, the inactivation gates are actually open. It's just the activation gates that are closed. Okay, if that makes sense. And this is just, again, as a summary of the action potential that you guys can look at. Some of you might like, I put different pictures in here because you might like different pictures for, different individuals. And you're welcome to print any of these off and put these on your mirror. This is a great one, actually, to print off and put on your mirror if it helps you out. Local anesthetics. Okay, local anesthetics and certain neurotoxins will actually prevent the opening of these voltage-gated sodium channels. And so this is how we use local anesthetics. So when you give something like Novocaine or lidocaine, you're causing in this area localized changes that are preventing that drug is preventing the voltage gated sodium channels to open while that drug is in that area. Okay, and so that's how they work. So again, Novocaine, which I actually read, for those of you that are in dental hygiene, is oftentimes now mostly lidocaine injected, actually, locally. But again, what this is doing is it's, again, numbing those nerves, especially, again, the pain nerves that we're most, concerned with, right? By, again, preventing those voltage gated sodium channels from opening so they can't pass down an action potential. So again, this is mostly important, right, for these pain sensory neurons, if they're, removing a mole or something like that. Okay. So that way then those pain sensory neurons can't send an action potential back to the brain. So you're literally not getting that sensory information for pain in that area. Pretty cool, right? Real quick, I know this has gone long, but I want to go ahead and try to finish with the continuous versus saltatory conduction. So again, continuous conduction is what we've already talked about in the unmyelinated fibers. It's that step-by-step depolarization along each portion of the axon, or what we call, again, the axolemma, across, again, that membrane of the axon. Now, saltatory conduction, for those of you that don't know the term saltatory, it means jumping. Okay. And so saltatory conduction means that we end up just having depolarization happen only at the nodes of Ranvier. Again, where there's going to be a really high density of voltage gated ion channels in that one area. Okay. You're going to have lots of them crammed in. And so what it's going to do is it's going to allow a lot of sodium to rush in, and so much so that it will bypass, right? It'll travel down and kind of flow down in the intracellular fluid to the next node of Ranvier, triggering those sodium gated ion channels to open. Okay. And so again, the myelinated area we're going to talk about, the myelinated area isn't going to have these voltage gated ion channels. And so what it does is it actually allows us to be a little bit faster, believe it or not, because what ends up happening is, instead of, having to go in this successive movement where this sodium gated ion channel opens, triggering this one, then triggering this one, okay, down this kind of successive movement. Instead, we have, again, these myelinated areas and these nodes of Ranvier, right, in between. And so what ends up happening is, once we hit a threshold stimulus here, again, it triggers these sodium-gated ion channels, and there's lots of them in these nodes of Ranvier. So lots of them to open, again, causing a really big change in the membrane potential that's going to flow, okay, and the intracellular fluid from this area. So sodium keeps rushing in, and then it's going to trigger this sodium gated channel over here to open, and these ones to open. So instead of having to trigger one here and here and here, now you're just triggering them here and here. And so it's actually much faster. It causes, again, that signal to be conducted at a much faster rate. Okay. So again, this is because there's a really high density of those voltage gated ion channels in each of the nodes of Ranvier. Okay, and the current is carried, again, by ions that are flowing through that intracellular fluid from node to node. So again, and it says extracellular fluid. This is actually supposed to be I'm sorry, I don't know how that got in there. It's supposed to actually be intracellular fluid. So because, again, we're causing, again, a change in the interior of the membrane here. So sorry, it's supposed to say intracellular fluid from node to node. Okay, so again, hopefully that kind of helps you make sense of saltatory conduction. So this is just showing you that jumping motion of saltatory conduction from node of Ranvier to node of Ranvier. The last thing here is just the speed of impulse propagation. Obviously, this makes sense that it would be faster in larger fibers, as well as obviously a myelinated fibers that allows that saltatory conduction. Okay, so the larger fibers and the myelinated fibers, axon fibers, are going to conduct impulses much faster. Okay, so there are actually different fiber types. Fiber type A is obviously going to be your fastest because it's your largest fiber in diameter. And then it's also myelinated. So this is going to be most of your, again, myelinated somatic sensory. Somatic, remember, is going to be those sensory that are going to the body, especially like the skin. Okay. So that's your somatic sensory. And again, that's going to be these A fibers as well as your motor fibers that are going to skeletal muscle. Okay, because again, that has to happen fast. So this is why, again, that sensory information when you're touching your pen and writing can happen very quickly, transmit that sensory information back to the brain very quickly, and then you could transmit that information right out those motor neurons to the skeletal muscles in your hands very quickly, okay, to allow you to make those quick changes in your fine motor movements as you're writing. Now, B fibers are going to be the kind of medium size and also, again, the medium paced fiber, right? So here, these ones are kind of your medium in diameter here, as well as, and you don't have to know the microns. You just have to know A is the largest in diameter, B is the medium in diameter. And these are myelinated, and these are going to go to your visceral sensory. So again, these are going to be the sensory neurons that are going to your organs, like detecting that your bladder has stretched, that kind of stuff. And then also as well as some of your autonomic neurons, okay? And I'm not going to focus on that too much right now because I know we haven't gotten too much into how the autonomic nervous system works and what preganglionic is. So again, I put it here, but we'll come back to that. And then C fibers are going to be the smallest ones. And again, these ones are going to be unmyelinated. So this is going to be your slowest fibers. So this is going to be your unmyelinated sensory, as well as your autonomic motor. Okay, so unmyelinated sensory, a lot of times this is going to be with things like your special senses and stuff. Encoding of a stimulus. How do we differentiate light touch again from firm touch? We already talked about this. I'm not sure I had this slide twice, but again, frequency of impulses. So firm pressure generates impulses at a much higher frequency. So boom, getting faster, faster stimulus, more again, at a higher rate. And that's going to be for firm pressure. And then obviously, again, for lighter pressure would be stimulus at a lower rate here. Okay. So the number of sensory neurons that are activated, again, oftentimes can also help you differentiate from firm versus a light touch. So obviously, if you are activating more, because you're putting a lot of pressure, you're activating more of those sensory neurons, then again, that's going to cause more of those gated ion channels to open. So firm pressure is going to stimulate more neurons, as well as it's going to stimulate more neurons in that area than does light touch. Okay, so those are the two ways that we can differentiate light touch from firm touch. Again, frequency of the impulses and the number of the actual number of sensory neurons that you're actually activating. So hopefully that makes sense. Okay, so I'm going to go ahead and stop on this slide, and then we will start up. I'll go over this really briefly in terms of muscle cells versus neurons, but I'm not going to spend too much time on that. And then we're going to talk about signal transmission at those synapses at the very end, and that will wrap us up for these series of lectures.